Right now, 13.14 billion light years from Earth, a telescope is staring at something that has no name in any textbook. It is not a star. It is not a galaxy. It is not a black hole. It is somehow all three at once, and it is roughly the size of our entire solar system. On August 12th, 2026, a team of astronomers led by Rohan Naidu published a paper in the journal Nature announcing the discovery of an entirely new class of astrophysical object. They call it a black hole star. The specific one they found is designated MOM BH star 1. And the reason it is sending shockwaves through the scientific community has nothing to do with hype and everything to do with a single uncomfortable fact. According to every model we have for how the universe builds things, this object should not exist. Here is why that matters to you. Right now, sitting inside nearly every large galaxy, including our own Milky Way, is a supermassive black hole. Ours is called Sagittarius, a star. It weighs about 4 million times the mass of the Sun. But here is the problem that has haunted astrophysics for over 20 years. We keep finding supermassive black holes in the very early universe, just a few 100 million years after the Big Bang, when there simply was not enough time for them to grow that large through ordinary processes. Something fed them far faster than physics should allow. And now, for the first time in history, we may have found the thing that did the feeding. If that sounds like the kind of story you stick around for, make sure you are subscribed with notifications turned on. This channel breaks down the most significant developments in space and science before anyone else. No filler, no recycled clips, just research. To understand what MOM BH star 1 actually is, you first need to understand the puzzle it solves. So let us rewind to 2022, the year the James Webb Space Telescope opened its golden eye. Within months of beginning science operations, Webb started imaging galaxies so far away that their light had traveled for over 13 billion years to reach us. These galaxies existed when the universe was an infant, roughly 400 to 800 million years old, and they were too bright, way too bright. Theorists expected faint smudges. What Webb delivered were vibrant, luminous structures that appeared far too mature for their age. Then astronomers noticed something else. Scattered among these ancient galaxies were peculiar objects that showed up as tiny reddish points of light. Compact, extremely red, extremely bright in infrared wavelengths, but nearly invisible in ultraviolet. By late 2023, the first peer-reviewed papers gave them a nickname, Little Red Dots. As of 2025, more than 300 little red dots have been cataloged across Webb's deep field surveys. They appear everywhere. Webb looks in the early universe, but seem to vanish by the modern era. Nobody agreed on what they are. Some teams argued they were galaxies, harboring overweight young black holes. Others proposed they were supermassive primordial stars in their death throes. The competing theories multiplied, and none of them fit all the data. That is the backdrop. Now, let us talk about what Naidu and his team actually did. Their project was called Mirage, or Miracle, or MOM for short. The question was simple. Are all of those impossibly bright early galaxies real? Or could some of them be optical illusions, objects whose brightness is caused by something other than starlight? Webb had imaged thousands of sources during previous programs, including a survey called Primer that used the mid-infrared instrument in January 2023 and the near-infrared camera in August 2023. Additional observations came from the X-Cells survey in December 2023. Finally, Naidu's own MOM survey targeted selected objects again in December 2024. Among the thousands of candidates, one source stood out. It was extremely red and extremely bright, appearing to outshine an entire galaxy. The team designated it MOM BH star 1. When Naidu's team analyzed the light from this object, two features immediately defied explanation. First, it was red. In astronomy, red typically means dust. Dust particles between a light source and a telescope absorb short wavelength blue light and let longer wavelength red light pass through, much like wildfire smoke turns a sunset blood red. But when the team examined the spectrum more carefully, the chemical signatures did not match dust. The redness was coming from something else entirely. Second, the object displayed what physicists call a Balmer break. This is a sharp drop-off in brightness below a specific wavelength where hydrogen gas absorbs photons. Stars that are a few 100 million years old show Balmer breaks. The bright star Vega in our night sky shows one. But the Balmer break in MOM BH star 1 was the deepest ever measured in any object, with a strength of 7.7. For reference, ordinary stars produce Balmer breaks with strengths around 1 to 3. No known star can produce a break that extreme. Something else was creating that wall of hydrogen absorption. And there was a third clue. The spectrum contained almost zero signature of metals. No carbon, no oxygen, no silicon, only hydrogen and helium. This ruled out an ordinary galaxy full of mature stars, because stars synthesize metals in their cores and scatter them into their surroundings over time. Whatever this was, It existed in a nearly pristine primordial environment. Naidu and his colleagues at the Massachusetts Institute of Technology's Kavli Institute for Astrophysics and Space Research ran simulations. They modeled different physical scenarios and compared the predicted light output to the light Webb actually observed. Could you make something that red using only hydrogen without any dust? Surprisingly, the answer was yes, but only under one very specific condition. You would need an incredibly dense screen of hydrogen surrounding the energy source, so dense that it behaves less like a nebula and more like the surface of an enormous star. This explained the Balmer break, but it did not explain the luminosity. The object was 100 billion times brighter than the sun. Nuclear fusion, the engine that powers every star we know, cannot produce energy at that scale in a single source. You would need the gravitational power of a black hole. So the team inserted an accreting black hole into their simulations. They varied its mass, the density of the surrounding hydrogen cocoon, and the accretion rate. After hundreds of model runs, they found a match. The best fit scenario is a central black hole approximately 100,000 times the mass of the sun. This black hole is actively consuming gas from a surrounding envelope of hydrogen and helium that extends roughly 40 astronomical units outward, about the distance from our sun to the orbit of Pluto. The entire structure spans roughly the size of our solar system, and the energy from gas spiraling into the black hole gets scattered outward through this dense envelope, producing the extreme redness and the record-breaking Balmer break that Webb observed. This is what Naidu calls a black hole star. The concept is not entirely new. In 2006, astrophysicist Mitchell Begelman at the University of Colorado first proposed the theoretical existence of objects he called quasi-stars. The idea was that in the very early universe, before metals existed, enormous clouds of pristine hydrogen could collapse directly into supermassive protostars with thousands of solar masses. If the core of such a star collapsed into a black hole before the outer layers could react, the surrounding gas might not explode outward. Instead, it would remain in place, forming an equilibrium where the black hole's radiation pressure holds up the envelope from inside, much like nuclear fusion holds up a normal star. For 20 years, quasi-stars remained pure theory. Nobody had ever observed one. The reason is simple. They were predicted to exist only in the first billion years of cosmic history, at distances so extreme that no telescope before Webb could have resolved them. MOMBH Star 1 sits at a redshift of 7.7569. That corresponds to a time 660 million years after the Big Bang. Its light has been traveling for 13.14 billion years to reach us, and it matches the theoretical predictions of a quasi-star with remarkable precision. But here is where the twist gets deeper. If MOMBH Star 1 is a black hole star, then what about all the other little red dots? Over 300 of them have been cataloged. They are not as bright as MOMBH Star 1, but their spectral properties, the redness, the Balmer breaks, the compactness, are consistent with the same physical model. The difference, according to Naidu, is that in those other cases, the surrounding host galaxy contributes some of the light. In MOMBH Star 1, the black hole star completely outshines its host galaxy, giving astronomers a pure, uncontaminated signal. If even a fraction of those 300 objects are also black hole stars, it would mean the early universe was populated by a class of object we never imagined. And it would solve the 20-year mystery of how supermassive black holes grew so large so quickly. A black hole at the center of a quasi-star could accrete gas at rates of up to several solar masses per year, potentially reaching 10,000 solar masses within the object's estimated lifespan of 7 to 10 million years. Once the hydrogen envelope dissipated, the exposed intermediate mass black hole would continue growing through mergers and standard accretion, eventually reaching the billion solar mass monsters we observe as quasars. Think about what that means. The black holes at the centers of the galaxies we see today, including the one at the center of the Milky Way, may have started their lives inside these structures, wrapped in a cocoon of primordial gas, hidden from view, quietly eating their way to dominance. Now, there are important caveats. This is a single object, and the black hole star interpretation, while compelling, is not confirmed beyond all doubt. The Nature paper explicitly states that the model fits the observed data better than alternatives, but follow-up observations will be required to rule out other exotic explanations. One competing theory suggests that some little red dots could be supermassive primordial population 3 stars of perhaps 1 million solar masses, observed in the last few thousand years of their lifetimes. Their spectra can also produce strong Balmer breaks and broad emission lines. Distinguishing between the two scenarios may require additional spectroscopic measurements with Webb or future telescopes. There is also the question of X-ray emission. If these objects contain actively accreting black holes, you would expect them to emit X-rays. But stacking observations from the Chandra X-ray Observatory have found very little X-ray signal from little red dots as a class. One explanation is that the dense hydrogen cocoon absorbs the X-rays before they escape. Another is that the accretion geometry is unusual. Neither answer is fully satisfying yet. What is clear is that before August 12, 2026, no one had ever identified a quasi-star in observational data. The word itself lived only in theoretical papers and simulation codes. Now it has a name, MOAM-BH Star 1. The paper has already accumulated over 21,000 digital accesses in its first 2 weeks. The altmetric attention score exceeded 800 within 3 days. Other research groups are already reanalyzing their own datasets to search for additional candidates. The implications extend beyond astrophysics. If quasi-stars are real, then the early universe was a far stranger, more violent, and more creative place than we imagined even 5 years ago. Objects the size of solar systems, powered not by fusion but by gravitational destruction, glowing with the luminosity of entire galaxies, existing in a pristine cosmos of pure hydrogen and helium, and all of them vanishing within 10 million years, leaving behind black hole seeds that would grow into the engines of every major galaxy in existence. We built a 6.5-meter gold mirror, launched it 1 million miles from Earth, and pointed it backward through 13 billion years of time. And what we found was not just an answer, it was a new question. If the universe can build something this strange, this powerful, and this brief in its infancy, what else is hiding in the data we have not analyzed yet? That is the thought I want to leave you with. If this video gave you something to think about, hit the like button. If you want to be here for the next discovery before anyone else covers it, subscribe and turn on notifications, and drop a comment below. Do you think quasi-stars explain the little red dots, or is there something even stranger going on? I read every single one. I will see you in the next one.